Hi guys, so in this session we are going to discuss the Codechef Starters 82. So we'll be discussing the first 4 questions or for div 1, that is different matrix, find x, make them alike, and tree game. So let's get started with the very first question. So the very first question is a very simple one, I'll say. So the question states that you are given an integer n and you need to find a n into n matrix such that each element of the matrix is an integer from 1 to n square, right? And the matrix is also square matrix. So yeah, 1 to n square should be each of the indices and they should be distinct as well. But the constraint over here is that the absolute difference between the neighboring elements should strictly be greater than 1, right? Now over here, if we check the constraints, then n at least is 4. So basically you will be at least having a 4 into 4 matrix, right? So in case if you are having a 4 cross 4 matrix, so what I can say is that firstly let's have all the positive firstly let's have all the values which are even, right? So this is the minimum matrix you are having, right? 4 into 4 is the minimum matrix you'll be having. So I'll say let's have the odd numbers first, maybe 1 3 5 7, then you have 9 11 13 15, right? And then let's have all the even numbers. So when you have all the even numbers, so they will be 2 4 6 8 10 12 14 and 16, and this always would be a valid answer. Now there could have been a problem in case your matrix size could have been like 2 cross 2. In that kind of a scenario, if you went for like 1 3 2 4, then this could have been a problem, right? But in this case, even answer wouldn't have existed. So but since we are having minimum of 4 cross 4 matrix, hence whenever we write all the even numbers first and then the odd numbers, then it would always satisfy. The reason being that when we'll conclude our even numbers, so we are concluding our even numbers over here, right, on this line, and then we are starting our we are concluding the odd numbers here, so these are the odd numbers, right? And then we are starting the even numbers. Now at the end of the odd numbers, the biggest values would be there, and at the starting of the even numbers, the smallest values would be there, right? So the difference would always be greater than 1, or you can even say greater than 2. Cool. And also, since we are taking the even numbers and the odd numbers respectively, so every consecutive element would have a difference at least 2. So that's why this case always satisfied. And so is the I don't even know why they give such problems in contests, but anyway, this is the code itself. So firstly we are printing out all the odd values, so these are the odd values from 1 to n square, right? And then we'll be printing out the even values. Any doubts in this? Cool. I don't even expect anyone to have a doubt in this. So let's talk about this question. You were having some doubts in this, right? And when I'll be discussing it, if you feel like you didn't understand something, then a point right over there, I'll try to explain it. Cool. So the problem states that chef has 4 integers a, b, c and d. A modulus b is equal to c modulus d. So that is something they have given us, and it is guaranteed that x always exists. And what is x? Now x is something we want to find, and it is the smallest positive integer x, such that a plus x mod b is equal to c plus x mod d, right? So that's it. That's what they have given us. Also over here, a, b, c and d can go up to 10 to the power 9. Hence a brute force application won't work over here. So you'll have to think in a different manner, because answer can actually, if I tell you the answer can actually go up to 10 to the power 9 or something of that sorts. So you'll have to think differently. So let's talk about the solution or the intuition. Now over here they are saying that you have to print the minimum x, right? Let me change the color. Okay, so when we are talking of minimum x, so they're talking that the x should be positive, right? So positive numbers start from 1. So definitely the minimum answer we can give is 1. Now in what all scenarios would 1 be an answer? Let's say we have 2 mod 5 and we have let's say 2 mod 7, right? Now in both these cases, 2 mod 5 is 2, 2 mod 7 is 2, this is a, this is b, this is c, this is d, right? We can simply say that, okay, add 1 to both of them. So we'll say 2 plus 1 mod 5 and 2 plus 1 mod 7, right? And this would give you 3, and this will also give you 3. So this is fine. But would 1 always be an answer? When would it be the case that 1 is not your answer? Let's check that also. So let's say the number I was having over here was 2 mod 3, cool, and the other number was 2 mod 7 as it was earlier, right? Now 2 mod 3 is 2, 2 mod 7 is also 2, but if I now add a 1, right? If I now add a 1 to it, so this becomes 2 plus 1 mod 3, that is actually 0, and this becomes 2 plus 1 mod 3, that is actually a 7. Oh sorry, that is actually 3. 2 plus 1 mod 7, that is actually 3. So now these don't become equal. So what I want to say over here is that as soon as you add a single number, right, and the number turns out to be 0, in that case either both of them should become 0. So it should have been the scenario that this and this term both became 0, then it's fine, right? But if one of them is becoming 0 and other is not becoming 0, then they won't be equal. Make sense up to this point? Or any doubts?
Yes.
Okay, cool. So this is something I know. So what I can say from this is that if my a mod b is less than b minus 1, right, and my c mod d is less than d minus 1, in that case the answer always is 1. Cool.
Yeah.
Mm-hmm.
Right.
Right. And the other case is that if my a mod b is equal to b minus 1 and my c mod d is equal to also d minus 1, in that case also the answer is 1, because as soon as you add 1 to this would become 0, right? And also this would become 0. So in these two cases the answer is always 1. Guys, can you turn off your mic? There's some noise coming. Okay. What's the remaining case? The remaining case is that, let's say for a mod b the answer is b minus 1, but for some other for the other value, that is c mod d, the answer you are getting is, let's say, something else, right? It's maybe it's something y. Cool. In this kind of a scenario, we need to find what the answer would be. Now over here the modulus we are taking is from b and d. So now if we take a LCM bd, right, it would be having some value. But note, since LCM basically means that it would be divisible by both b and d, so technically when I'll say a plus LCM, okay, LCM bd, right, okay, I hope my writing is understandable. Let me write this again. If I'm writing a plus LCM of bd, right, and then I take a modulus with b, so this would basically means if I expand it out, so this means this, right, LCM bd mod b, right? Now since LCM of bd basically means the lowest common multiple of bd, that obviously is divisible by b, so this would give me a 0 and this would give me a mod b, right? Same would be the case with a plus c plus LCM bd mod d. This would also give me c mod d. So what I can say is that the answer is LCM minus LCM bd. Okay, LCM bd minus a mod b, or you can say c mod a mod b or c mod d, both have the same values. Now why is this the case? Because I'll say that I'll plug this particular equation into my answer, and what I'll be getting is a plus LCM bd, right, minus a mod b, right, mod b. So if I expand it, this becomes a mod b, right, minus a mod b plus LCM bd modulus b, right, and then this would get cancelled out. Its value is 0. So in both the scenarios you are going to get in the LHS as well as in the RHS, you are going to get a 0, right? This maths is clear? Guys, any doubt over here, or this is clear? Since you're not speaking up, I am assuming that there's no doubt in this. So I'll be moving ahead and I'll just show you the code. That's what I'm doing over here. I'm checking these two conditions, that either both of them, right, that a modulus b should be less than b minus 1 and c modulus d should be less than d minus 1, or both of them should be equal to it. In that kind of a scenario, my answer would be 1. If this is not the case, then my answer is LCM bd minus a mod b. Cool. So this code was also simple. Let's move ahead to make them alike. Now make them alike is I won't say is a difficult question, but people got confused in some weird weird scenarios. But let's talk of the problem statement first. So the problem statement is that you are given a permutation p of length n and an array a of size n and an integer m. Now initially all the values in a are greater than or equal to 0 and less than or equal to m. Consider array a dash obtained from a by replacing all the zeros in a with the positive integers less than or equal to m. So wherever you have zeros, you can replace them with any value that have to be positive, so they cannot be zero again, and they need to be less than m, less than or equal to m. And this a dash would be your array. Now you will transform it as follows. So in the ith step, you'll set a of I is equal to a dash p of I. Cool. Now what's this p of I? This is another array they would have provided you. So this is p of I basically. Cool. Now okay, let's get over here. Yeah. So yeah, basically that's the question. Now you have to tell them that how many beautiful arrays a dash are possible to make using these operations, right? Now what's the criteria for array to be beautiful? So that is another problem. So array is beautiful if all the elements in it are equal, right? So let me show you that with the help of an example. So let's say we are having the permutation 2143, right? Now what would this do? So let's say 2143 is obviously given over here, right? And the array we are having is 0202. So basically these are the two elements that we can replace with some other values. So let's say we replace the first 0, this is this one, with the value 1, and the second 0 with the value 3. Now let's see what happens. Now a1 dash needs to be replaced by ap dash. Now what's the value of p? P of 1? P of 1 is 2, right? So we'll replace it with a2. So over here in this particular array that we formed, right, 2 is 2, a2 is 2, sorry. So you'll assign a1 as this value, then you'll come to 2 and you'll say that okay, what's the permutation at that particular place? So that is 1. So we'll say let's assign it a1. A1 has already been set to 2, right? So that's cool. Then we'll go to 3. Then we'll say that okay, I want to set a3. What should I set a3 to? A3 should be set to whatever value is at index 4 of a. Now let's see what is the value of value at index 4. So value of at index 4 is 2. You can take this from this step. You'll assign 2 over here. Then you'll go to a4 and then you'll say that okay, in a4 I have to assign the value at index 3. So the value of index 3 is actually 3. So you assign 2 over there. Cool enough? So this is one of the valid permutations. Like this you can have a lot of permutations, right? And you have to print them. Now they have also mentioned that the permutations can be large, so you have to take a modulo 10 to power 9 plus 7. So obviously it should ring a bell that you cannot actually do a brute force approach over here. That's definitely gonna fail. Now what else can you do? Let's talk of that. Let's talk of some intuitions. So what you can say is that if this is your array, right, and let's define the array in terms of like maybe some cycles or maybe some graphs or some edges, right? Now this is my array. If I'm saying that my permutation at I is equal to j, that basically means that my I or this particular element I is going to take the value of j. Now if my j is before I, then I don't care about it. Why is that the case? Why won't I care about it? Definitely is in my array, right? I have to care about it. But the thing is that when we'll be building our answer, we'll be going from left to right. Cool. And since we are going from left to right, if my left value has already been set to the correct value, then its value would also be set to the correct value, right? So this automatically would become true, or the value at I would automatically become true or become valid if the value of j was valid. Cool. And we are traversing from left to right, so let's not worry about I, let's just worry about j. Cool. Now what are the two cases? So basically I said that whenever your I is pointing to a value that is before you need not worry about it. So let's not worry about it. No worries. Cool. The only worry is that when your I would be pointing to a value that is ahead of it. Now let's say your I is pointing to some value j that is ahead of it. Let's call it k maybe. So k is actually ahead of it. Now you need to worry about this. Now, what are the two cases that can happen? So it could be that your value at k is either 0 or your value at k is either non-zero. Now in a case where the value is 0, then you have an option of changing it. If your value is not 0, then you don't have any option, no options. Cool. Now if you don't have any options, then the only thing you need to know is that all the case. So let's define, okay, let's call points, or let's call points important. Let's denote it by p of imp. So pimp, or this is becoming pim, but yeah, anyway, let's just call it pm. Cool. So pm are the points where some value is depending on you. So let's say if this is your array, right, and based on the permutations, these are the edges that you're getting, right? Let's say these are the edges. We are not concerned about the back edges, so let's not bother about that. We are only concerned about the forward edges, right? Okay, let's not make that edge. Okay, let's make this kind of edge, right? Okay, so over here I'll say that okay, these are the backward edges, these ones, right? So I'll not bother about them. I'm only concerned about the forward edges. So based on my forward edges, this particular point, and this particular point are the important points I'm having, right? See, these are the only points that actually matter to me. So for all these points, I'll firstly see which of these points actually have a value 0, right? How many points of PM have value 0 and how many have a value non-zero. Okay, how do we represent non-zero? Maybe like this. Cool. So how many have a value 0 and non-zero? Because wherever you are having a value 0, you can change that, right? But non-zeros you can't change. But wait, what if there are multiple non-zeros? So it could be that this is an important point. This is also important point. Now it could be the case that this is like these two have different values. So maybe like this particular value has 6, this has 7. Now there's no way whatsoever that you can construct a valid permutation out of it, or you can make this array beautiful, because 6 would get stored over here, right? Because it will fetch its value from here, and 7 would get stored over here because this particular node would get its value from here. So there's no way that your array is going to be similar. So that leads me to my first conclusion, that if you are having more than, okay, or you can just simply say if two values are different and they are non-zeros, right? Then in that case, your answer does not exist. So this is my first observation. Guys, any doubt so far? And in case someone is typing, so please just let me know, because I'll not be opening this chat box. Cool. So if someone is typing, just let me know. Cool. So this is my first observation. The second observation is that in case, let's say now two values were not different, right? But you still had some value over here. Now what would happen in that case? In that case, let's say your fixed value was something like 6, right? Now all the values that are over here that are also 0 needs to have a value 6 also, right? Because they are also some other values dependent on them, and since all the values in the beautiful array needs to be same, so this also needs to needs 6 values. So what are the values that we can change? So the values that we can change, or we can put anything over there, would be the ones wherein your like you are having a val 0 which is not important. Now we define the important values as the values wherein some at which some other value was depending, right? So like this particular node was depending on this particular value, so this was important. So the red one is important, right? So all the nodes which have a value 0 but are not red, or which are not important, would be the ones wherein we can put any value. So we can put any value from 1 to m in it. From 1 to m, any values can be put over here. What about the other nodes? So let's say this one, so the one first condition we already did over here. This was like the answer would be 0. The second condition is that some of you had a fixed value present, right? Or let's say fixed value present. So in this case, all your non-important zeros, right, these can be filled by any value. So fill any value over here. The third case is that there's no fixed value. Now for all the zeros that are important, you have a choice of keeping like putting any value over there from 1 to m. So now in this case, you'll be having two values. So one is value 0, which are important also, and over here the other category would be value 0, which are not important. So in the value 0 which are important, you need to put any value from 1 to m, but it should be same. Now it cannot be the case that there are two slots that are important, right? By important, that means that they are giving you the values to some other locations, and in one of them you like keep 1, in other of them you keep 2. It cannot be the case. So if you're keeping 2, you have to keep 2 in both of them. If you're keeping 1, you have to keep 1 in both of them, or whatever value x you're keeping, that needs to be in both of them. Cool. So you can put any value from 1 to m in them, and for all the zeros that are not important, in all of these you can individually put any values. So their sum actually would be m to the power of numbers. Cool. Because each of them would be having m possibilities. So you can simply say m into m into m into m, so on, right? And then you will just multiply it by m over here. This makes sense. I hope the code was clear. Let's just look at the solution also. The solution is also kind of simple. So what I'm doing over here is, firstly I'm taking the two arrays, that is the like the permutation vector, permutation array, and the vector or the vector a. Then I'm saying any. Now what do I mean by any? Any is actually the number of indices where I have 0. So any basically means I can put, okay, put this in this. Cool. Then I'll be saying fixed. So what do I mean by fixed? That I have some fixed values. Initially I'm setting is to false. Let's just hope that there are no fixed values and I can make any sort of permutation I want. And then there's this dep. Now what's dep? Let me discuss that later. Cool. Then firstly, since I'm using zero-based indexing, so I'm decrementing my permutations by a single digit, because permutations were given one-based indexing. Then I'm saying that if the current element is 0, then update my any. If your current element is greater than or equal to I, because I said that whatever values are before you or are to the left of you, you need not be concerned about them, right? So you only need to check for values which have a dependency on the values at your value or after your value, right? So if it's greater than or equal to I and the value at the particular permutation is not 0, in that case you have a fixed value, right? Cool. So this means, okay, pointed to a fixed value. Cool. After that, you'll say that if your value was already fixed and the value that was fixed is not equal to this value, that means you technically have two values now. Cool. In that case, you can say that your answer does not exist, just print 0 and return. If that is not the case, so you can put a else over here, but doesn't matter since you are using a return. Cool. If that is not the case, then set your fixed to true and then set the value also. I'm setting the value equal to the value that would be at the location that it's pointing to. And now if your if your dependent node is to your right or at the current location, but that value is 0, in that case I already found some value that is 0 but is also important. Cool. I hope that makes sense. So these are the values that are important also and are to your right. Cool. So I'm inserting then in dep. You can actually use you can directly use a variable over here. I initially was doing some debugging, so I used dep, but you can just use a variable and you can increment them. Now I need to check for the 0 values at which I can put any sort of value, right? So that would be the values which are not important but are zeros. So that would be given by any minus dep. So I can actually change the change this like I told. But anyway, so any minus dep dot size, that would give me do any or put anything over here. Put anything. Okay. Now there are two cases. So one case was already handled over here as we discussed. Now there are two cases. One case is that you have some fixed value. If you have some fixed value, then only for this do any zeros you can put any value from m, right? So basically that would be m to the power of number of zeros you are having. So that would be your answer. If that is not the case, now power over here is not the standard function that you have in C++. It's something that I have written on my own. This is just so that I'm able to handle modulus operations and overflows. Cool. So if that's the case, just print that. Else, for all of the numbers, right? Now what is m over here? Now that's another thing. Now what's m? M basically is the number you can keep, right? From 1 to m you can assign any values. So you'll say that for all the zeros, now since the value is not fixed, right? So for all the 0 values that are not, that are important to me, I can keep any of these m values, right? But it has to be consistent. So if I'm keeping if I'm keeping one of the important indices as 1, then or as x, then the other index also needs to have a value x, right? M into the same thing. So for the other zeros that are not important, I can put any value, and then I'll just multiply them and take them out. Cool. So that was it for the question make them alike. Let's move ahead to the final question, that is tree games. Now, I actually did this wrong in the contest because I was missing a few edge cases, right? Or my algorithm was not handling the edge cases well. But over here, I'll be discussing the optimal solution, and this really is actually a very very short code and even shorter than the one we just did. So the problem states that there are n cities numbered from 1 to n connected by n minus 1 roads such that every city is reachable from every other city. The ith city has the population pi. Alice and Bob are initially standing at cities A and B respectively. They decide to play a game such that at every turn, first Alice makes a move by moving to some adjacent city by unvisited by her. That could be visited by Bob. Cool. And then Bob also makes a move, so he'll be also moving to a city that is unvisited by him, right? And whenever they reach a city, so their score becomes the total population in the path from where Alice started and from Bob started. So Alice would say that okay, I started from a city A, currently I'm sitting at A dash, right? So whatever was the entire population in this entire path from A to A dash, that's my answer. Bob would also say the same, right? So if the answer that Alice is having or the score that Alice is having is strictly greater than the score that Bob is having, in that case Alice is rewarded a point. If that doesn't happen, then Alice is not rewarded a point. And as soon as the case happens that either of these players is unable to make another move, right? So they won't be able to make another move whenever both of them would have like no adjacent cities left which are unvisited, right? Whenever that happens, then the game immediately ends. Now Alice and Bob both play optimally. You have to tell that what is the maximum score Alice can achieve. So initially this question might look a bit complex, but looking at the constraints, if you look at the constraints, then n is just 5,000 over here. They've also mentioned that across all of the test cases it won't exceed 5,000. A n-square approach would definitely work over here, right? Now since they are talking of a graph and not a tree, so over here even the number of edges are limited to n. Now when I'm saying n-square, basically I mean standing at every edge, I'll be computing every path, right? So that so basically we just need to imitate the game. So we just need to do what the game actually is doing. We just need to code that up and we'll get the valid answer. So let's look at the code because I don't think there's a point in explaining anything about it, wherein what you have to do is actually just code it up or code it exactly what the algorithm says. Cool. So over here we'll be taking three values, n, a and b. Then the standard way of taking a graph is over here. Cool. Then you call a DFS and that would be your answer. But how will you call a DFS over here is that you'll say that what are initial nodes. So Alice would be standing at A, Bob would be standing at B. Do they have a parent node? So right now we just started. So let's put some dummy value. So -1 is the dummy value because -1 is a value no other node would be having, right? Also sum of A or the score of Bob, score of Alice and the score of Bob. Along with that, I'm providing the graph and the vector wherein the values are stored or the population of each city is stored. After that, I'll say that okay, now Alice is at city A and Bob is at city B. So let's provide them with the population count of that city. But since we are using zero-based indexing, so I'll be using doing a -1 zero-based indexing. Okay. Cool. After that, I'll say let's set my result to 0. Okay, yeah, that's fine. And then the score would be 1 only if sum of Alice is greater than Bob, correct? So if that's the case, then I'll assign score 1. If that's not the case, then I'll assign a score 0. Now there is a case that one of the player has already reached a point from where he cannot move to any adjacent city which he has not traveled. But this won't definitely be the case if PA is not equal to -1, right? If PA is equal to -1, that basically means you have just started. Cool. So just let me explain that a bit because this can become a bit confusing to some people. So if you just started, okay, that wasn't intended, but never mind. Okay, so if you have just started at a node, let's say this particular node, and it has connections with some several nodes. Cool. Now you can say that okay, I've started from this node. My adjacency list for this particular node is actually having a size 1, so I can move to this node, right? And you can say I can move to this node. Let's look at the sizes now. Over here adjacency list size is actually 2. Over here it's also 2. Let's call it 2, 2. Over here it's 1. Now as soon as you move over here, so basically if you have a adjacency list size of 1 and you already came from another node to this particular node, right? So that would mean all your paths from where you could have traveled to this node, or what all your cities from where this city is connected to have been traversed, right? So that's what I want to check. So whenever your adjacency list size would be actually 1, AD size would be 1, that would mean that you have already traveled or you have already traversed all the adjacent cities, right? Or all the connected cities. But this won't be the case with the starting node itself, because at the starting your connected nodes are not visited. Cool. That is something I'll be checking over here. So I'm saying that if PA is not equal to -1, or if it's just not the starting node, and now the size of any of the cities of let's say Alice or Bob's, or any of the adjacent list of Alice or Bob is actually 1, then I can just return from there itself. I cannot move further, or the game has stopped over here. Else what I can say is that Alice can select any of the cities she wants to go to. Cool. The only exemption would be that she cannot go back to the city she just came from. So that is an exemption. And then Bob can also go to any of the cities. So let's say Alice goes to a city. Cool. Or Alice selects a city, CHA, child of A, I'm saying. So you can like give variables some better names. So if she goes to a child of A, now Bob would know this, right? So Bob can also go to any city. But now we have to check for all the permutations, because what Bob would try to do is he would try to minimize the answer, because Alice has already moved, right? So Alice would say, I've already moved, I'm already going to CHA. Now it's Bob's turn, and Bob would try to minimize the answer. So Bob would say, let me try for all the possible cities that are reachable from me, right? And I'll try to set the minimum possible answer from this. So Bob would say that initially we'll take a variable cur that would be having a big value or int max over here, and we'll try to minimize this value as much as possible, or let's say Bob would try to minimize this value as much as possible. So that's what we are doing over here. We'll set the value of cur to minimum of cur of whatever the DFS would return us. If Alice goes to the city child of A, Bob goes to the city child of B, right? And then the parent cities would be A and B, obviously, and some A and some B are the values they are going to pass. Other than that, these are the static values we are passing. Cool. After that, now when Bob says that, okay, I've tried all the possibilities, this is the minimum score I can, or this is the like the minimum score Alice can get if I play optimally, right? So let's store that value. I'll tell Alice, or I'll tell my system that this was the value I was giving you. But Alice would say no. So I have a lot of opportunities, right? I'll try for all of these cities that are connected to me. So I'll select the maximum answer from this. Cool. So over here, Bob was doing this operation of minimizing. So he was saying minimum of both these two. Alice would always try to maximize her answer. So you'll say result is equal to maximum of both of this, right? Your current result that was initially set to 0, right? Or whatever you're getting over here. After that, you'll say that your final result is score plus result. I hope this makes sense and this was understandable. Cool. So yeah, this is for the solution. You can, I'll just mention this code when I upload this video. Cool guys, if there's any doubt you can let me know. I'm gonna pause this video right over here. Cool guys, thanks a lot. Bye bye.